Okay, so we did a linear factorization problem in the last example video, and this is the one that we did in class at the next class, and so this one involves complex zeros instead. So in this problem, instead of giving you a graph to look at, I just tell you that one of the zeros is z equals 1 minus 2i. So you can do a couple things with this. One of the things you can do is you can say, okay, then I know one of the factors is going to be x minus 1 minus 2i. And you also know that since 1 minus 2i is a 0, then you're also going to get the 0, also get z equals 1 plus 2i, because they come in complex conjugate pairs. So then you also are going to get this as a factor, x minus 1 plus 2i. Well, we need to get all of the zeros. So one thing you could do, and if you prefer doing it this way, that's fine. You could take these two guys, you could multiply them together, get a quadratic with only real coefficients, and then do f of x divided by whatever quadratic you end up with, and you'll get another quadratic, and then you can factor that. Instead, what I'm going to do is something like we did in the last video, which was take our 0 and use synthetic division with it. So since we'll look at this factor first. Since that's my factor, I should be able to use synthetic division. This would be 4. Notice there's 0x cubed, so 0 here. 17x squared, 14x, and 65, just constant units. And then over here, my 0 is 1 minus 2i. Remember, it's x minus k, so the k goes there, so it's x minus 1 minus 2i. So you get to work this out exactly the same way. It's just a little bit messier. Well, by a little, I mean probably a lot. So the 4 comes down, and then I do 1 minus 2i times 4, which is going to be 4 minus 8i. And then I add down. So 0 plus 4 minus 8i is 4 minus 8i. And then I need to do 1 minus 2i times 4 minus 8i. And this is where I recommend kind of working some stuff out on the side here. So if I work this out, then you're going to end up with, let's see, 4, and then minus 8i minus another 8i, so minus 16i. And then negative 2 times negative 8 is 16. So it's plus 16i squared, which is really like minus 16 here. So we get 4 minus this 16, which is negative 12, and then minus 16i. So that's what goes here, negative 12 minus 16i. And then when I add straight down, it's like 17 plus 0i plus negative 12 plus 6i. So 17 plus negative 12 is 5, and 0i plus negative 16i is negative 16i. So now I got to do it again. 1 minus 2i times 5 minus 16i. So over here on the side, 1 minus 2i times 5 minus 16i. So if I work that out, that's going to be 5. 1 times negative 16, and then with another negative 10, that's negative 26i. And then 2i times 16i, negative becomes positive, 32i squared, which is really like negative 32. So it's 5 minus 32, negative 27, minus 26i. So that goes here. And then when I add straight down here, I get negative 13 minus 26i. Now remember, this is a quick way to help you check. This we know is a 0, which means this remainder here has to equal 0. And if it doesn't equal 0, then we've made a mistake, which also means that this value here should be negative 65. So let's check it. So if I do, let me switch back to red. If I do 1 minus 2i times negative 13 minus 26i, well, let's see. So I get 1 times negative 13 is negative 13. I get 1 times negative 26 is negative 26i. I get 2i times 13 negative, so that's positive 26i, which is good because now these guys cancel. And then I got negative 2i times negative 26i, which is plus 52i squared. which is really negative 13 minus 52, which is negative 65, equals, equals, equals. So I get negative 65 here, so this is 0. My remainder is 0, which is good, so I'm going to make a happy face. Okay, so I've now factored out the x minus 1 minus 2i, and this would be my constant term here, the negative 13 minus 26i, 5 minus 16i x, 4 minus 8i x squared, and 4x cubed, which is still pretty ugly to deal with. But I do know that I have another 0, 1 plus 2i. So I'm going to continue this problem. I'm just going to extend my division right here. If you prefer to make a new chart altogether, that's fine. Notice I'm not including the 0 because that's already done. So now I'm dividing by 1 plus 2i instead. So the 4 comes down again. And then 1 plus 2i times 4 is going to be 4 plus 8i. And when I add straight down, I just get 8. And then I multiply 1 plus 2i times 8, and I get 8 plus 16i. And I add straight down, and I get 13. And then I do 13 times 1 plus 2i, and I get 13 plus 26i. And I add straight down, and I get 0, which I'm supposed to get because I know this should evenly divide in. So equals 0. That's good. Happy face. All right. So at this point, I basically factored out this and this from my f of x. So I can write f of x as x minus 1 minus 2i, x minus 1 plus 2i, and then what's left over, which is 4x squared plus 8x plus 13. By the way, once you do the first term, the first complex term that you, or non-real term that you end up having to do the synthetic division with, you can see you get a lot of ugly stuff here. When you do the second one, the complex conjugate, that should clean up everything down here. And if you end up with I terms down here, then you did something wrong. So make sure that that's a nice way to check to see if you're on the right path. It doesn't tell you if you're exactly right or not, but at least it's a good check. And also, these remainders should always be 0 if you know you're plugging in zeros to begin with. Okay, so we're not done factoring because this is a quadratic, except that one doesn't factor easily by hand. So in order to get the zeros of this, let's, so let me write this. 1 zeros of 4x squared plus 8x plus 13. So in order to get that, we're going to use the quadratic formula. So let's set it up so it equals 0. 0 equals 4x squared plus 8x plus 13. And then I can use quadratic formula, which is going to be negative b plus or minus square root of b squared minus 4ac all divided by 2a. And I can tell you now that this is negative 8 plus or minus root negative 144 all over 8. This whole root here turns into just 12i. So this is going to be x equals negative 8 plus or minus 12i over 8. And then that simplifies into negative 1 plus or minus 3 over 2i. So I know that the zeros of this quadratic I can write as negative 1 plus 3 over 2i and negative 1 minus 3 over 2i. And remember, these are related to the factors. The factors are going to be x minus that and x minus the other one. But so this is actually intercept form now, except I've lost the leading coefficient of 4. So I'm going to come back to that in 1 second. So at this point, I can now write f of x as those first two factors, right? So x minus 1 minus 2i, x minus its conjugate, and now I've got these two guys here. So let me just do this. There. Okay. And remember, I lost that leading coefficient, which was all the way back up here. I'm supposed to get 4x to the fourth. And down here, if I multiply this out, the biggest term I'm going to get is x times x times x times x, which is only regular x to the fourth, 1x to the fourth. And the way to fix that is just throw the 4 in front of the entire thing, and then you're good to go. So this right here is the linear factorization of f, and the zeros are 1, or let's say x equals 1 plus or minus 2i, and negative 1 plus or minus 3 over 2i. So there are 4 zeros. They all happen to be non-real, which means this thing never crosses the x-axis. So I don't know exactly what it looks like, but let's say the x-axis is here. It's an x to the fourth. It probably does something kind of like this. And I don't know where the y-axis is really, but I know that it goes through at 65 somewhere. So, but again, I'm not positive it looks like that. I just know that it never crosses the x-axis. So, okay, I hope that helps some.